Thank you. Okay, Zoe.
Thank you. Right. So I'm going to teach this course on finite and pseudo-finite fields. The first lecture will probably be very easy for many of you. I mean, I guess if it's too easy, you should tell me. And the other thing I wanted to mention is that actually the way the course is scheduled is a bit strange. It will not be every Thursday. The reason being is that next week I won't be around. And also there will be a workshop the following week. So the schedule will be apart from today, right? I will write it down somewhere here, like for instance here. So the next session will be on November 22nd. This is a Monday at 11 a.m. Then you will have November 25th, a Thursday, again at 11 a.m. And finally, the 9th of December at 2 p.m. The reason for this 2 p.m. is that in the morning of, on that week, you will have the Coxeter lectures by Udi Hruszowski. And we decided that to have the lecture on December 9 will take place at 10 a.m. And we thought that, to have two lectures back to back was a bit much, and to have, especially, Udi's lectures contain a lot of things, so we need to digest it. So that it would be better to have my lecture at 2 p.m. in the afternoon. Okay, so that's that. And so what I'm going to talk about, so it's some of the early results on the model theory of fields and pseudo-finite fields. So first of all, what's a pseudo-finite field? It's an infinite model of the theory of finite fields. So these were studied by Axe in the late 60s. And he showed the decidability of both theories, and he explained how, he described, elementary invariance and all kinds of things and a sort of quantifier elimination. Well, actually, here I'm slightly lying. It was more Kiefer who did the quantifier elimination. But anyway, so in that time, lots of things were done about these fields, finite fields and pseudo-finite fields. Decidability was shown, and so on and so on. Then I guess the next results, well, okay, Duret showed that any PAC field which was not separably closed had the independence property. So you will soon see what a PAC field is, okay? These are fields which are nice, but they have the independence property. Right, apart from that, they are very nice. Okay, and then I guess the next important results were obtained by Udi Hruszowski and then later in collaboration with Anand Pillai, whom we know, about the fact that showing results which actually amounted to the fact that the theory of pseudo-finite field was super simple, and all kinds of nice results and all kinds of very nice applications to the theory of either finite fields or pseudo-finite fields. So anyway, I will talk about these results, and then if I have time in the last course, I will talk about what's going on, more recent stuff, okay? I guess I should also mention is that the theory of pseudo-finite fields led to an intensive study of the theory of PAC fields. First of PAC fields with so-called bounded absolute Galois group, and then of PAC fields in general. So I guess the first results were obtained by Jardin and Quinet on E-free PAC fields, meaning that the absolute Galois group was free profinite on E generators. Then there were results of Jardin on omega-free PAC fields, again, describing them, showing actually that these fields, there are quite a lot of them in nature, in particular as algebraic extensions of Hilbertian fields. Okay, so there were lots of things being done, and then you studied those guys. I mean, there was a lot of activities on PSE fields and stuff like that. Okay, let me start with finite fields. So, so please stop me here if because I'm going to really do the basic. So a finite field, as you can imagine, it's going to contain a prime subfield which has to have characteristic a prime. So will contain a field isomorphic to Z mod PZ, simply because any field contains 1, 1 plus 1, and so on, and it only stops if a multiple of 1 is 0, and if you are in a field, that multiple has to be a prime. Okay, so, and that field is actually denoted by FP. All right, so this means that a finite field is going to be an FP vector space. All right. So an FP vector space has cardinality P to the n. So I cannot yet say that it's unique, but well. So let us put FP inside a large algebraically closed field of characteristic P. All right. So inside K, you have that. So let me call my function field here F. Then you see that the cardinality of my finite field F, the cardinality of the units of F is going to be P to the n minus 1, right? Simply. So this implies that every non-zero element satisfies the equation x to the P to the n minus 1 equals 1. In other words, every element of F satisfies x to the P to the n minus x equals 0. All right. If you look at this equation, and if you derive it, you take the derivative of it, you are, so the derivative is P to the n, x to the P to the n minus 1, and you see that this is always going to be minus 1, so it's never 0. This means that the roots of this polynomial are all distinct, and in fact that this polynomial is exactly the product for A in F of x minus A. All right? All the roots are simple. There are P to the n of them. This gives you, when you take that product, it gives you a monic polynomial. This has to be it. All right. So now you can see that, of course, this uniquely describes F. There is no other subfield of K with P to the n elements, and we will note F as F sub P to the n. All right. Okay. So what else can we say about these things? So inside the field of characteristic P, we have seen already that the Frobenius map, which sends x to the P, well, this is, of course, a multiplicative homomorphism in any field, right? But in a field of characteristic P, it's also additive. So in other words, it's always going to be a ring endomorphism. In a ring which is an FP algebra in any FP algebra. Okay. A commutative, I guess, maybe is better. All right. In our case, well, as we saw, it's a multiplicative map. It has kernel 1 as a multiplicative. I mean, on the set of units of F, it has kernel 1. I mean, it's injective, so therefore it's an. Okay, why on 2? Because you are dealing with a finite set. Okay, so this actually this means that this is a generator of the Gara group of Fp to the n over Fp. I mean, why is it a generator? Well, it's an element of the Gara group of Fp to the n over Fp. And in fact, one shows that this is the only one, not the only one, that this generates the Gara group of Fp to the n over Fp. Let me give you something else, which is that it actually comes from there, but you see that here we have x to the p to the n minus 1 equals 1, right? For every element which is in the multiplicative group. So you can wonder, so we know that this group is abelian. One of the things that you get is that actually it is cyclic. If it wasn't cyclic, right, then it would have an exponent which is a strict divisor of p to the n minus 1, all right? Which means that and moreover, you would have some equation of the form x to the m minus 1, which would have 2 roots. But this is impossible because all the roots are simple. All the roots of x to the p to the n minus 1, they are distinct, simple. So therefore, all the roots of a divisor of m dividing p to the n minus 1, x to the n minus 1 are also going to be simple. Okay, you won't have 2 roots. So therefore, this implies that the group is cyclic. Of course, is cyclic of order p to the n minus 1. So that's useful too. And then it follows that this map is onto, is a generator, because you see that p is prime to the order of f cross. All right. So therefore, it's going to induce a permutation. Okay. Okay, so what I claim now is that the algebraic closure of Fp is the union of all Fp to the n. All right. So that union being, it's an infinite union, and you have Fp to the n contained in Fp to the m, if and only if n divides m. Why? Because if you contain a subfield, if this means that you are a vector space over that subfield, and hence you need to have that p to the n divides p to the m, and this only happens if n divides m. Rather, no, not that p to the n divides p to the m, but that you are a power of p to the n, and that only happens if n divides m. Okay, so this tells you how to put all the fields inside each other, right? And it tells you what the union, so the algebraic closure of Fp in K is this thing, all right? So why is it everything? It's just because if you have some element which is algebraic over Fp, All right. Well, the field it generates over FP will be finite, therefore it will be one of those. Okay. So therefore it contains every element which is algebraic over FP. Okay. So that's easy. Okay. So, so the power, if you take a power of the Frobenius map, say x goes to x to the p to the d. So what is going to be the fixed field of this? You see that it's the element which satisfies x to the p to the d minus equals x, right? And you see that this is equivalent, this is exactly fp to the d. Okay.
The field inside the
K.
field?
Yeah, inside K. Or inside any overfield. All right. Okay, so now you know everything about this, and I guess I can tell you now that the Galois group of FP alg over FP is what is denoted by Z hat. It's equal to the inverse limit of the field of the groups Z mod nz for n greater than 0, okay, in n. You can also view it as the product over P L prime of the groups ZL. Okay, you know that each ZL, it's another way of looking at ZL is that is as the inverse limit of the Z mod L to the N Z. Remember? Okay, so this is all right. So this is what's also called the free group on one generator. I guess I should be more precise, free profinite group on one generator. So if you see what it is, if you look at the topology on Z, whose open subgroups are the subgroups of finite index, all right, then this is the completion of Z for that topology, all right? So there is such a notion of profinite completion for any kind of group. Given a group G, you look at the collection of normal subgroups of finite index, and you put the topology which is generated, the group topology which is generated by those subgroups of finite index, and then you can define the profinite completion of G, of that group G, which is usually denoted G hat, to be the inverse limit of all the quotient by these subgroups. Okay, let me write it down. So you have G a group, you look at the collection N of all normal subgroup of finite index. Okay, and you look at G hat, which is the inverse limit of the G mod N for n in N. Okay. And this is the profinite completion of G. You don't necessarily have that G embeds into that. It will only embed if G is residually finite. But nevertheless, this completion exists. It could be, for instance, I mean, if you look at Q, what is Q hat? What is Q hat? Zero. Q hat is 0. Okay, well, so not every group has a interesting completion. Nevertheless, all the free groups have interesting profinite completion, And so Fe hat will be the profinite completion of the free group on E generators. Here E is in N. F omega hat is a little more, it's actually contrary to what I'm saying. It's, well, I guess I should maybe denote it something different. F omega bar is the what's called the free group on countably many generator. So here you impose in addition that actually finite index and N contains all but finitely generators. Okay. So, I mean, then it would be, you know, it's G hat would be defined with respect to those generators you have chosen. In the case of omega hat, you take the standard generators, and in a sense, it's going to be the inverse limit of the Fn hat. Well, it's the same. Okay. One can define it in two ways. Okay, so let's write. You see, the free group, free profinite group is also defined by a certain universal property. And okay, if you really took the profinite completion, if you allowed all the subgroups of finite index, actually you would get what's called the free group on 2 to the F0 generators. So it's too big. Okay. Questions so far? I mean, this is baby stuff, right? Okay. I'm not going to, shall I mention this result of X, which I find fantastic, and I'll let you find a proof? Because you, right. So I'm going to state an easy version. So theorem X. So it's an easy version. Let F bar of X bar be an n tuple of polynomials over C, C the complex numbers, where X is an n tuple as well. And assume that when you evaluate F bar on C to the N, it defines an injective map Cn to Cn. Then F bar is surjective. So this is an exercise. I'm going to give the hint. If instead of C to the N, you had the algebraic closure of Fp, would that be true? Yes. Yeah, because you see, if you have the bunch of polynomials defined over the algebraic closure of Fp, well, they are defined over some Fp to the m, right? And then the fact that the map is injective means that it's injective on Fp to the m to the n, right? But that's finite. So if it's injective, it's surjective. Okay, right. So it would be true for Fp bar. And now what? Now what? Okay, well, I'll let you finish the proof. Okay, so the thing is, what we are going to do now is that we are going to axiomatize the theory of finite fields and pseudo-finite fields, okay? So let me give you the axiomatization and then we will discuss it. So we are going to consider the theory PSF star, so which has, of course, the theory of field, which says that the field is perfect. Everybody knows what a perfect field is. So in other words, if 1 plus 1 plus etc. plus 1 p times equals 0, then for all x, there exists a y to the p is equal to x. All right. Then an axiom, which I'm going to call 2L, which says that the field has exactly one extension of degree L. And finally, axiom 3MND saying that the field is PSC. For every M and D tuple of integers. So that's a scheme of axioms. Then there is going to be TF star. Say something. Yes, all these schemes of axioms. Yes. So then you have TF star, which is so perfect plus 2L. And something which is I'm going to call 3' MND, which is going to say that, well, I'll tell you later. Provided, okay, so I guess, let me say it. Every absolutely irreducible affine subvariety of what? Okay, I mean, so D is the degree, M is probably the number of polynomials, and N must be the number of variables of A to the N, defined by at most n polynomials of degree less than or equal to D, has a solution provided the cardinality of the field has sufficiently many elements. Okay.
And solution means there's a point to divide.
Has a solution in Fn. Okay.
When you mean has a solution, you mean has a point to divide.
Yes. Has a point. Has a point in Fn. Has an Fn rational point. An F point. Okay. Now, except for the last condition.
Zoe, what is C?
C is a constant.
Ah, so there is some constant such that, right?
There is some constant.
Okay.
Which depends on M and D. Okay. So, except for the last condition, this is exactly to be PAC. PAC says a field is PAC if every absolutely irreducible variety defined over the field F has a point with coordinates in F. All right. Now, in order to say that, of course, you need to quantify over all possible irreducible, absolutely irreducible subvarieties. To do that, you quantify over the coefficients, but you need to be able to say that they're absolutely irreducible or not. Okay, so I'm not sure if you want to see all the details of how one can axiomatize this. Anyway, I'm going to start with how to say that these axioms are first order. So axiom 1 is clear, right? I basically gave it. For axiom 2, well, I'm going to say the following. If f of x and g of x are irreducible over f, right, of degree n, then f of x divided by the ideal generated by f of x is isomorphic over f to f of x divided by g of x. In other words, as soon as you contain the root of f of x, you are going to contain a root of g of x. All right? And it turns out that this will suffice if we can express this. Because, well, you take, remember, we are in a perfect field, so every finite extension is generated by just one element. So you can take, let's say, if you have a Galois extension of f of degree something, let's say L or not. And you take a generator, you take its minimal polynomial, well, then you know that that Galois extension will contain all elements which are of degree L or dividing L over F, okay? And so it turns out that this shows that it has exactly one extension of degree L, and this shows that its Galois group is Z hat. Its absolute Galois group is Z hat. So how can you express this? You see that f of x is of degree L. So this thing is an F vector space of dimension L. Okay? So addition is done by coordinate by coordinate. What about multiplication? Well, with the help of f of x, with the help of its coefficients, so let me write f of x as what? As, you know, this is the kind of thing which is trivial, except that if you don't do it right, okay. F of x equals x to the L plus sum equals 0 to L minus 1 of x of AL x AI x to the I, right? So when you multiply an element by x, so every element will have coordinates. So if alpha is a root, then it will have an element will have coordinates in the basis 1 alpha, alpha squared, etc., alpha to the L minus 1. Okay. If you multiply an element by alpha, one of those bases, well, everything gets shifted by 1 except alpha to the L minus 1, So alpha times alpha to the L minus 1 is going to be alpha to the L, which is going to be minus sum from I equals 0 to L minus 1 AI alpha to the I. All right? So with this, you see that you can interpret multiplication. All right? You know how to multiply by alpha, therefore you know how to multiply by alpha square, alpha cube, and so on. All right? Good. And you see, furthermore, what's important is that it's uniform in the coefficients. All right? So if I have another things where another polynomial g of x, which is defined by x to the L plus sum of bi xi, it will be exactly the same. And if I know that it's irreducible, okay, to say that it's irreducible says that it's not the product of two polynomials of lower degree, right? So that's easy to say. And well, then you will have exactly the same kind of formula. You will have that if beta is a root, then beta times beta to the L minus 1 is equal to minus sum of the bi's alpha I, of beta I, sorry. So you see that the matrix which gives multiplication by alpha, by beta, has exactly the same shape as the matrix which says multiplication by alpha, okay? It's just the last column which changes, and it's changed in a totally uniform way. So which means that you can say this, all right? You can say this easily. Okay. Absolutely reducible. I guess I'm going to do a little bit of baby algebraic geometry. Very baby. So no schemes, no nothing. So we are going to work in Fn or An of F, whatever you want. Let's call it. It's usually denoted by An. But so work in Fn. Inside Fn. So F now any field, okay? So you have an algebraic set is defined as the zero set of a bunch of polynomials, of some polynomials, over F in F of x1, xn. Okay, so you have, of course, if you have F1, Fm in F of x1, xn, if you look at the set of points on which these polynomials vanish, this is your typical algebraic set. Okay, obviously, if you have a point in there, any element of the ideal generated by F1, Fm will also be in that, will also vanish on those points, right? So you can look at I of V of F1, Fm, which is the set of elements in F of x1, xn, which vanish on V of F1, Fn. I mean, more generally, when you have a subset S of Fm, you can do the same thing with F vanishing on S, and this is called the Zariski closure of S. When you go back to Zariski closure, okay. So in general, when you do this operation, right, you do not land on the same set, you do not land on So first of all, you get, certainly, it will contain the ideal generated by F1Fn. It will also contain its radical, right? Because if F to the K vanishes, then F vanishes. It's actually bigger in most cases. I mean, unless F is algebraically closed, it's bigger. All right. Okay. So this gives a topology on F to the N, which is actually a Noetherian topology. So you have a notion of irreducible components. So these are going to be the closed sets, right? You have a notion of closure. This is going to be, so if you have a set S, then if S is contained in F to the N, then V of I of S, this is the Zariski closure of S. You all know that, right? So the youngsters, what about the youngsters? Do they all know that? You don't know it. That's true that you are the youngest man of the... No, but I'm thinking of, I don't know. So is this, everybody finds this trivial? You? Yes, it's, you know it. Stefan, you know it? Okay, so then I'll just go quickly then. So you have a notion of irreducible component, okay? You have a note, so they correspond, of course, to things where the ideal is going to be prime. All right. Now there is the question of enlarging the set of the base field. So if instead of F, you go to the algebraic closure of F, it could be that your thing, which was nice and irreducible, is not irreducible anymore. Okay. Absolutely irreducible says that actually that even when you go to the algebraic closure, it's going to stay irreducible. Okay. And in our case, it is just because we are in the case of a perfect field. In our case, it means the following. In the case of a perfect field, in the case of perfect F, if V is an irreducible affine variety over F, so this exactly means that if you look at, if you define F of V to be F of X bar modulo the ideal of things which vanish on V of F, okay, modulo the defining ideal, which is going to be prime, V of F bar, that F defined by some prime ideal P, if you look at it, you define the affine coordinate ring of V to be F of X over P. And then because your variety is irreducible, you know that this thing is a domain, so you can take its field of fraction. So let's say that F of V is generated by some little X bar. Okay, so the corresponding to those coordinates mod P. And then you have that V is absolutely irreducible if and only if F of V contains no element which is algebraic over F and not in F. all right? So this is just, I mean, if you think about it in terms of generic point, if you think of this X as a generic point of the variety, V, this is saying that the field generated by X bar over F does intersect trivially the algebraic closure of F. I mean, intersects the algebraic closure of F in F, all right? So this is fairly, right. So absolutely reducible means
Zoe,
okay.
I have a question. So this equivalence is because F is perfect, right? I mean,
Yeah.
it's not always true, and this is because of linear disjointness being the same as the
Yeah.
intersection being okay.
Yeah. Yeah, in the case of non-perfect things, you have strange things happening, okay? For instance, yeah, you have strange things happening, all right? I'm going to stop now for 5 minutes. Is that what I'm supposed to do, right? Okay, and I'll continue. And I guess in the second part, I'm going to give you an idea of how the scheme of axiom for 3 works, okay? Yeah, I think you can erase everything. Maybe not these. Yeah, leave that. But all the rest, yes. Thank you.
In general, linear disjoint only implies that intersection is.
It says that when it's perfect, I mean, in general, okay, listen to me. In general, if you intersect a Galois extension trivially, then you're linearly disjoint. Okay, so that's all.
So this happens the other way.
It happens always. So if F is perfect, then F algebra is Galois. You see, but it's fairly easy to show. You know? It's,
I need to remind myself.
yeah.
At my age of it.
Ah! I should turn off my, because they can hear me, right?
You can ask them.
Are you hearing me?
Yes, we can hear you.
I'm not sure that it's just a question of. That was my point. Because usually you read it sentence, but I guess it might just not sure. So why not? But you're sure that it's not. have to check with the family and see. But so we'll do that and we'll yeah. You get
Can you hear me? Paul?
Yes, we can hear you.
Okay. Shall I start again? Everybody's here? Anand has disappeared. He knows all that stuff, you know. Very much. Okay, so we've seen how to do axiom 1 and axiom 2L. What about axioms 3, M, and D? Okay, so first of all, the M is a bit unnecessary because we are looking at, so in the same way as we could interpret, you know, a finitely generated F algebra inside F, well, I mean, if you look at the set of polynomials in n variables of degree less than or equal to D, well, this is not quite an algebra, but it's certainly a vector space, an F vector space of finite dimension. So obviously you can interpret addition. When you interpret multiplication, well, of course, you are going to land. I mean, if you take two polynomials of degree less than or equal to D, they're going to land, their product is going to be of degree less than or equal to 2D. Okay. So this means that you can sort of interpret f of x1, xn inside f, but with what's called bounded quantification. So you can say things about given polynomials of degree less than or equal to D, there exist polynomials of degree less than or equal to k, such that blah, blah, blah. So for instance, so the first question which happens is you have f1, f. So first of all, the m does not matter because it's going to be, m is going to be less than or equal to the dimension of the f vector space of polynomials in x1, xn of degree less than or equal to d. Okay, so m, you know that it's bounded. So the question arises already. So you have f1, fm of degree less than or equal to d. Can we say in a first order way in the coefficients that some g, also of degree less than or equal to d, belongs to the ideal generated by f1, fm? So what does it mean that G belongs to the ideal? This means that there are H1, Hm, such that G is the sum of the Hi, Fi, right? Fine. But if you cannot, in order to be able to say this in a first order way in terms of the coefficients of the Fi's and G, what you do is that you need a bound on the degree of the Hi's, right? Okay, so there is a theorem. I guess I'm going to say, give the name Hermann. So there is, so G of degree, there is a bound which depends on, as I say, n and d, such that the Hi can be found of degree less than or equal to n to a. Okay, so this means that it becomes a first order statement if you knew that G was of order less than or equal to D. Okay, now then what's the question? Fine.
And the F's, I guess, also the
I'm sorry?
generators. The generators are also bounded by degree. The Fi's are also bounded by the same, by D.
Yes, everybody's bounded by D. Like here, n polynomials of degree less than or equal to D. Okay. So the first thing to say is, well, you need to know about belonging to the ideal generated by. Okay. M is the number of elements. No. N. N is the number of variables. M is the number of polynomials. Okay. D is the degree of all the polynomials I'm looking at. All right. Okay. Second thing, what about saying that F1 Fm is prime? Okay, how do you do that? So again, F1 Fn of degree less than or equal to D. What does it mean it's prime? It means that if GH belongs to F1 Fm, then either G or H belongs to F1 Fm, right? Okay. Now, fine. But again, you need to bound the degree of the possible counterexample, okay? So there is B equals B of ND such that if the ideal I, which I'm going to call it I is not prime, then G and H can be taken of degree less than or equal to B. Okay? And this together with the fact that here you have blah, 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 this is okay, right? I mean, because you know how to say, now you are going to replace D by B, okay? And you're going to check, all right? Yeah, everything is Hermann. I guess it was also later done by Seidenberg and things like that. So then there are other results, okay? I guess you have an F1 Fm. You want to look at its irreducible component, okay? So you know the irreducible component, well, they correspond to minimal prime ideals containing F1 Fm. Well, again, you will find a bound on the degree of possible generators for these and the number of all these. I mean, so you can do lots of things, okay? I'm not going to use these, not just now, but I'm mentioning it. So there is a whole thing, a whole array of things you can do. But already here, so you see that we now know how to say that F1 Fm define an irreducible variety, right? We already know how to say that. How do we say, and by a sentence which does not really depend on the field, okay? So there is a sentence, a formula. The formula in the coefficients of the thing, which does not really depend on the field, and which says if you satisfy that formula in that field F, then you define an irreducible variety. Okay? So there is a formula phi of coefficients of the Fm. So you take some kind of enumeration of the monomials and blah, 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 which is only such that K satisfies phi of A bar if and only if the algebraic set defined by the tuple of polynomial associated to that tuple of coefficients is irreducible. Okay, or if and only if actually sorry, I should say that simply the f of x ideal generated by the FA is prime. Okay, same thing. Okay, so that means that the variety is irreducible. Okay, so what's the trick? Remember, it's not irreducible that I'm interested. I mean, it's not that the ideal is prime, it's that it stays prime when you go to the algebraic closure of K. Right? Sorry, typo. Well, what do you know about the algebraic closure of K? No. What do we know about the algebraic closure? You see that such that for every K, gratify elimination, absolutely. So ACF says that psi of x is equivalent to psi of x bar, where this is quantifier free. Okay? In other words, what am I saying? There is a quantifier free formula which is going to tell you whether the ideal generated by the FA bar is prime when you look at it over K bar of x, over K algebra x, all right? So this means that we can quantify over, we can talk about absolutely reducible varieties. So this psi of A bar will tell you exactly those which are absolutely irreducible, okay?
Zoe, so you didn't end up using this perfectness and the linear disjointness trick in the end, right?
No.
No, okay.
No. Well, I'll use it later, certainly. No, it was just an easy way of telling you, of saying why, you know, an easy way of saying that something is not absolutely reducible. And also of seeing what the irreducible component will look like. You see, there will be really conjugates of the thing. All right. So you see now, we see how to say the 3M and D. Okay, actually the M does not really matter, but really the N and D, we know how to say this, okay? So given N and given, well, we know that given N and D, there is a band on M. So therefore, well, we have a bunch of possibilities, and there is, we're using this B to find a formula which tells you that, which is going to work for the ideal generated by this. Then you look at the quantifier free formula, which is equivalent to it in ACF. You get a quantifier free formula, and this is going to tell you that your ideal is or is not absolutely prime. Yes. It's too far, I can't see.
Why did you need a 3 prime?
Well, gee.
Sorry.
I'm not talking about 3 prime at the moment. I'm talking about 3. No, okay, so let me give you an example of a variety which is obviously absolutely reducible, right? And which does not have any solution in every finite field. Look at the variety which says that y times product for I less than j of xi minus xj minus 1 equals 0. So I is less than j, and it's varying between 1 and n. Okay, so what does this say? If you are a point in this algebraic set, right? Then your first n coordinates are all distinct, right? And you see that it's clearly an absolutely reducible variety, right? I mean, this is okay. So can this variety always have a point in a finite field? No, because if n is bigger than p, it doesn't have a point in fp. So this 3' is going to tell you that every absolutely reducible variety has a point, provided the field is sufficiently large. Okay, by sufficiently large, I still mean finite, but not small. Okay, and this actually comes from a result of Weil, which I'm going to state fairly soon. Okay. All right, let me see something. I'm going quite fast. This is good. I hope it's good for you too. Right. So let me. So one of the very important results, which is at the crux of everything. So as I said, I mean, it's clear that finite fields will satisfy 1 and 2n, right, by what we saw before. So as the example I gave tells you that it's not going to satisfy 3m and d in all generality. So the question is, when is it going to satisfy it? And actually, are the infinite models of the theory of finite fields going to satisfy it? And this is going to be followed from the theorem of Langevin. For every positive n and d, there is a positive constant which depends on c and nd, such that for every finite field fq, so q in the power p to the n, and absolutely irreducible variety defined over fq by polynomials of degree, variety contained in fq to the an. An is a fine space, right? And by polynomials of degree less than or equal to d, we have the following thing, which is that if you look at the cardinality of the set of points in V with coefficients in FQ, and you subtract from it Q to the power dimension of V. I did not define what was dimension of V. I will soon. In absolute value, this is less than or equal or less than, okay, C Q to the dimension of V minus 1/2. Okay, what's the dimension of V? You see that remember I defined So you have a V, right? You have your absolutely reducible variety, which is defined over something, over some field K. And you look first at its affine ring, which is K bracket V. And then because it's irreducible, you look at the fraction field. And this has a certain transcendence degree over K. And this is the dimension of V. All right? Okay. So in other words, this is the maximum number of coefficients of a point that you can choose and get, you can choose arbitrarily and still find a point in the algebraic closure. Okay. Good. So that's the dimension of V. Okay, what is this saying? You see, it's saying that the number of points in FQ minus a certain power of Q is less than a constant times a smaller power of Q. Now, when Q goes to infinity, you see that, so this is, you see that this is much smaller than this, okay? So if square root of Q is bigger than C, you see that then V of FQ is not empty. All right. So not only it's not empty, but when Q becomes large, it has lots of points. So this tells you two things. I mean, it tells you 3' ND with that very constant, all right? And it tells you that in infinite models of TF star, you will have that 3 of M and D holds unconditionally. I mean, holds, period. Because it will have more than C square points, okay?
Excuse me.
Hmm?
Is there a condition on the coefficients of the polynomials defining the variety in the theorem?
They have to define an absolutely reducible variety.
But the coefficients are in FQ or in Z?
In FQ, yes. Defined over FQ.
Okay.
Okay, other questions? This is really the theorem. This is, I'm sorry, I see that this is the theorem that's going to make much of what I'm going to say work, okay? So it was first proved by Vail for curves. So you would get, and I think he actually managed to, he computed effectively the constant in terms of the genus of the curve, okay? Right, I suspect that, I mean, for varieties, this constant is also effective, but okay, I'm not totally sure. All right, so anyway, a corollary of this is the theorem that every finite field is a model of TF star, and every pseudo-finite field is a model of PSF star, where pseudo-finite means infinite model of the theory of finite fields. At this point, we still don't know that TF star is really the whole theory, or equivalently that PSF star is the theory of all pseudo-finite fields, okay? There are actually some stronger results than these. So these were all these results were obtained in Access paper. Yes, why am I saying that every pseudo-finite field is a model of PSF star? It's just because if you look at the what's the elementary class generated by the finite fields, okay? So you of course have all the finite fields, then you have all the ultra products of finite fields, and then you have the elementary substructure of these guys, right? And when you have a non-principal ultra product of finite fields, it's going to be obviously infinite. All right. I mean, yeah. Okay. So we get that all. Right. So then the question is, do we have them all? Does TF star imply? Is it equal to the theory of all finite fields? And this will follow from certain number theoretic. Yes.
Why is it infinite? Why the pseudo-finite field? Why does it satisfy field F?
So, well, I mean, you see that every infinite model of TF star will satisfy PSF star, no?
Well, the condition is that.
Oh, the condition of the five.
I mean, okay, that's all. All right, yes, okay. So the question is this really the whole theory? I mean, we showed that every finite field satisfies TF star, but is it enough? And I think equivalently, it's the same to show that every PSF star, every model of PSF star is the elementary equivalent to an ultra product of finite fields. All right. Actually, one can prove something better. And I guess, right. Let me do something. I'm going to state a result, which is in a simplified version, which is called the embedding lemma. Which is very useful, actually. And embedding lemma, very simplified version. So we have let K, E, K star, perfect fields contained in some large algebraically closed field omega, and such that, maybe I should have said it in terms, really said it, but okay. K is a subfield of both E and K star. It's relatively algebraically closed inside K star and inside E. K star is a model of PSF, is Aleph1 saturated. E is countable. Has at most one extension of each degree. Then there is a field embedding. There is a K field embedding E inside K star. So so let me call it phi, such that the relative algebraic closure of phi of E inside K star is phi of E. So it looks a bit strange, this thing, a priori. So let's try to see what it says. So first of all, these are just saying that you have K star here, you have K, you have E. All these extensions are what's called regular, right? In fact, so you know that K star is pseudo-finite. So that means that its gamma group is generated by it's Z hat, right? Procyclic. So because the gamma group of K star projects by restriction onto the gamma group of K, this is what this condition says. All right. Then you know that the gamma group of K is also procyclic, an inverse limit of cyclic subgroup. And the condition on E also that it has at most one extension of each degree. This also tells you that the gamma group of E is procyclic, and the fact that it's regular means that it projects onto K. So you have this thing, you have this diagram. G of K star is isomorphic to Z hat, right? And because G of V is procyclic, actually, you can find a map here, which such that everything commutes. Okay, and right. So this is part of a more general framework where instead of looking at things with procyclic gyro groups, you look at other things. But anyway, what this is saying is that under these conditions, so let me write here my K star, there is a map here, okay, such that K star is going to be a regular extension of phi of E. So you see, for instance, so in particular, G of K star will project onto G of phi of E. G of phi of E is going to be isomorphic to G of E, so certainly the condition of G of E being procyclic is necessary. This will allow us to say that if we have a regular extension of our field K, we're able to embed it inside K star and in a relatively algebraically closed fashion, provided the gamma group of that extension is not too big. Okay, good. And this has for corollary the following result, which is the result due to Kiefer. So Kiefer is the one who really started doing, she generalized the work of Axe. Axe told you that the coefficient, that the completions of PSF star were given by describing what is the subfield, what is its intersection with the algebraic closure of the prime field. Okay, so what are the elements of your field F which are algebraic over the prime field? Okay, so either a subfield of the algebraic closure of Q or a subfield of the algebraic closure of FP. It can be, for instance, the whole algebraic closure of Q. So theorem, which is due to Kiefer, a little after, let K and L pseudo-finite field containing a common subfield K. Then K and L are elementary equivalent in the language of rings augmented by constant symbol for the elements of K, if and only if there is an isomorphism between the relative algebraic closure of little k inside big K and the relative algebraic closure of little k inside L. So you see that the difficult condition, I mean, certainly this is true, okay? Why is this true? Well, you see what you have to do is, well, you view this intersection as a union of finite algebraic extension of little k, right? And I mean, you show this has to be true for each finite algebraic extension of little k contained in K, all right? That it has to be there as well. It has to, that the other thing has to be there, all right? So in other words, if how am I going to call it? If K1 over K is finite Galois, then you certainly have to have that K1 intersect K has to be isomorphic to K1 intersect L. Okay, this is clear.
Zoe, why is that enough for the algebraic closure? To know it for every finite one, because maybe we have to.
Well, then there is a compactness argument which tells you that they are isomorphic.
Okay.
Okay. I mean, it has to do with the fact that, right, that you see that it has to do with the fact that the Galois group of K, profinite Galois group of K, right, G of K, is pseudo-finite. So therefore, it's actually compact. So when you have, it means that if you have an inverse limit of non-empty closed sets, well, it will be non-empty. All right. Okay, so that's how you do it. Okay, I can do it later if you want. I mean, it's. Or do you want me to do it? Okay. Right. So of course, the difficult condition is this one. All right. And the point is that we are going to pass to elementary extensions of K and L, which are sufficiently saturated, which are L1 saturated. Okay, and then you start making a back and forth argument. So we may assume little k countable. Okay, because if this is false, well, there will be a formula that will witness it, and that formula only has finitely many elements of k, so we may assume k countable. And passing to elementary extension, we may assume that k and L are L1 saturated. Now you are going to look at the following system of partial isomorphism. Where equals the collection of all partial isomorphism. So isomorphism. Between A and B, where you have A contained in K, B contained in L, A and B countable, and you assume that, so there are subfields, of course, subfields, A countable subfields, right? yes, contain K. Actually, these are K isomorphism, right? And we impose that A alg intersect K is equal to A, and B alg intersect K, intersect L is equal to B. Is this all? So you see, I'm looking at isomorphism, K isomorphism between countable, relatively algebraically closed subfields of K and L respectively, all right? And I want to show that I has the back and forth property. Okay. And this will be enough, right? Okay. Why is this going to be enough? Because I say so. But apart from that,
This shows much more than having the same theory. It has the same L omega.
yeah, it's
L
just
infinity
yeah,
omega.
they are yeah, right. I mean, it's just it's just a generalization of a Freise game, but to a non-relational language. That's all. Okay. All right. So once you do that, you have that this will be enough. Okay. And how do you do this? I mean, using this embedding lemma, this is actually quite clear.
So you're conscious of the time, right?
I'm sorry?
I'm checking that you're conscious of the time.
Okay, so proof, use embedding lemma. Okay, let me just write the thing. Okay, let me just write it. So we have A, which goes to B. B is inside L, right? Which is LF0 saturate. I want to do a fourth thing, which means I'm going to take an A prime, which is contains A, which is contained in K, right? Relatively algebraically closed in K. Therefore, it's countable also. Therefore, its Galois group is procyclic, all right? And therefore, I'm exactly in the situation of the embedding lemma. You see, this is going to be my E. This is going to be my K. Well, okay, whatever. So from this thing, this means I can do something there and send it to some B prime, which is relatively algebraically closed in L. Okay, this is exactly what it is. Okay, I'm stopping. Sorry, I went over time. But this gives you one direction. Of course, the other one is the same. Okay.
And next week we don't. Is it? Yeah, right.
So next week, no talk. Ah, the thing has disappeared, right?
Right.
So the next session will be on the
Monday.
25th, right?
Right.
Same time, 11. Thank you.
And then
This, because this is a regular extension. I mean, the fact that this condition, right?